Hi folks, we're going to talk about equilibrium and acid-base reactions. So this is a good example of what we're going to talk about, things happening on both sides. So the guy is shoveling one way and the other guy is shoveling the other way. And so the level of dirt on either side of that fence remains constant. And that's what we mean by equilibrium, that the forward and reverse reactions remain the same. So some things we're going to talk about is what defines something in chemical equilibrium. We're going to talk about different types of acids and bases, so things like Bronsted-Lowry acids and bases, as well as traditional acids and base definitions. We're going to talk about reversibility, Le Chatelier's principle, conjugate acid-base pairs, things that are amphiprotic, which means that they have more than one hydrogen, equilibrium constants, buffers, indicators, and we're going to revisit titration again, which everybody should have some knowledge about because we just did it in redox. So when we talk about equilibria, we talk about the forward and the reverse reaction happening at the same time. Oh no. At the same time. So in this example, we start here on the reactant side. So when we start the reaction, everything starts out on the reactant side, and there are no products. So this is before products are being formed. So no products here. As time moves on, most of the substances become products. So here we have the reaction moving to the right, and so we call this the forward reaction. So as it moves from reactant to product, it's the forward reaction. So it moves towards the products. So I'm just going to do forward. FWD. FWD means forward. When that has reached the maximum that it could possibly reach, the reaction's going to start moving towards the left. It moves in the reverse reaction, and this happens to reform those reactants. But the total number of moles remains the same, right? So I start with, let's count. 1, 2, 3, 4, 5, 6, 7, 8. I still have 1, 2, 3, 4, 5, 6, 7, 8. I still have 1, 2, 3, 4, 5, 6, 7, 8. So the number of moles remains the same. We're just seeing the reformation of those reactants. So it's the reverse reaction. RVS, reverse. And we call this reaction in dynamic equilibrium because what we see is the forward and the reverse reaction happening at the same time. So the total amount of moles remains the same. But they just go forward and backwards. And when it hits this stage, we say that this reaction has reached equilibrium. So let's recap. If we look back at our little guys over here, this is the forward reaction. That is way too thick. This is our forward reaction. Our guy is shoveling one way over the fence. He's turning all of that reactant into product. And then this guy on this side is the reverse reaction. He's turning that product back into reactant. Now let's talk about systems and what we call a chemical system. So a chemical system comes in 3 different flavors, sort of like flavors of ice cream. The first is an open system, which just basically means that it's open to air. So it's open air. It's like a beaker with no lid, right? You have a beaker, it has no lid, you have a reaction happening in here. That's what an open system is. The second flavor is called a closed system, where the matter is trapped inside, but energy can go in and out. So that's like a beaker or a cup with a lid on it. And so it has a lid on it here that keeps the matter inside, but we can release heat. That's hard to see. So it has that lid on it, stops things from going in and out, but heat can be transferred one way or another, depending on whether this is endothermic or exothermic. And the third flavor of reactions is what we call an isolated system, where no matter or energy is exchanged. So the best example on Earth that we have is an insulated container. So we have insulating materials with a high R value. Just R value just means how good they are at being insulators. That stops heat transfer. And when we're talking about energy in these systems, typically we're talking about heat transfer. If you're a physicist, you can also say things like the universe is a closed system. Because Earth can lose energy or gain energy, but the universe can't. But like I said, the best that we can come up with on Earth is an insulated container, which means like a thermos. So what are some assumptions that we make when we talk about these chemical systems? So the first assumption that we make is that chemical reactions are fast, right? We're just assuming that. We're also assuming that all reactions are spontaneous. We're not assuming there are no non-spontaneous reactions. So we're not talking about reactions that occur in electrolytic cells. And that they're all quantitative, which means that they go to completion. So 100% products and no limiting reactions are left. We also assume that they're stoichiometric, which means that we can predict the amounts of products since they go to completion. And that's what we've been talking about in terms of reactions so far, except for this electrolytic cells. So up till now, we've been making those assumptions of chemical systems. Now we're going to talk about chemical systems that don't go to completion. So I'm going to change the color. So many chemical reactions don't go to completion. They are in this state of dynamic equilibrium. So let's break down those two words. Dynamic means actively changing. And equilibrium means that there's a forward and a reverse part of the reaction. So this cartoon up here represents dynamic equilibrium because you have two guys throwing dirt over each side of the fence at the same speed. However, if one guy was going faster than the other, the piles of soil could be different sizes, and you could have different rates of forward and reverse reaction. All of these things that we're going to be talking about in this unit. When we talk about equilibria and we talk about chemical reactions, we talk about the things that we can see and the things that we can't see. So microscopic is things that we can't see. Too small. So our microscopic properties are things that are continually changing in our reaction. So these are reactions that occur on the molecular level. Our macroscopic properties are things that we can see. So these are constant. We might think that nothing is changing because those macroscopic properties are constant at equilibrium. So these are the things that we can observe or measure, things like temperature, color, and pH. This is an example of dynamic equilibrium because you have these molecules and their water evaporating and condensing, and they just go through that cycle of evaporation condensation over and over again. These are the macroscopic changes that we see. Not macroscopic, microscopic. Is the evaporation condensation. But the microscopic changes, or the macroscopic changes, like volume or pH, is the same. Because this is a closed system. So the water volume is going to stay the same. The weight of this is going to stay the same, or the mass. We're not going to see that evaporation condensation necessarily. And I'm going to in dynamic equilibria, there is a balance between the forward and the reverse reaction. So these exist together. These occur at the same rate. So that means that the properties that we can see or observe remain constant. How do we show that something is in dynamic equilibrium? we use 2 arrows in our reaction. So there's a couple of ways that we can show this. If the arrows are of the same length, that means that the forward reaction is equal to the reverse reaction. They're happening at the same rate. If the reverse reaction arrow is much larger than the forward reaction, we say that the reverse is greater than the forward reaction. That's what that means. If the forward reaction is much larger than the reverse reaction, that means that the forward reaction is greater than the reverse reaction. Easy peasy, right? That just shows that sometimes we can also have numbers here. So we can say greater than 90%, less than 90%. We can say equal to 50%. Sometimes we add numbers, but typically we just do big arrows, little arrows, because like I said, chemists don't love to write very much. How do we know that something's an equilibrium reaction? We'll always see 2 arrows. These 2 arrows indicate that this is an equilibrium. So this reaction, RxN means reaction is in equilibrium. Awesome. How do we use chemical or theories in chemistry to explain this? Well, one of the theories that we use is collision theory. So it explains that the reverse reaction can occur. Products can react to reform those initial reactants in the final state of the reaction, where the final state of the reaction is a competition. So the forward and the reverse reaction are competing together to determine which is going to be the most prevalent species. So when a system is in dynamic equilibrium, the concentration, so the square brackets mean concentration, of reactants and the concentration of the products will not change once equilibrium is reached. However, the forward and the reverse reactions continue to happen simultaneously. This allows our macroscopic properties, or the things that you can see. I'm just going to draw a little eyeballs there to remind me that these are the things that I can see are constant, but there's a lot of change that's happening on the macroscopic or the microscopic level. So these are things that I can't see. So what are some requirements that I need to ensure that my equation remains at equilibrium? So I have to keep a constant temperature. So because the temperature changes, and this Kc is the notation we use to indicate equilibrium constant. Also, what I have to do is make sure that the system is closed. So I have to, here's my Erlenmeyer flask, I have to put that stopper in. I have to make sure that nothing escapes. So it's a closed system. What we do know about systems in equilibrium is that physical and chemical changes can reach equilibrium. And we're going to go through a couple of examples here. When we're talking about solubility, so how things dissolve in water, for instance, I'm going to say H2O if it's a polar substance, in which case this is saturated solutions with excess solids. So here I have a beaker with water. I'm going to put a lid on it to make it a closed system, and I'm going to draw cubes of salt. So these are NaCl. What is happening is it's releasing NaCl, sodium and chloride ions, while at the same time NaCl, the solid compound, is reforming. So when it is saturated, the number of sodium and chloride molecules that are produced are the same as the amount of salt that is reformed. That's what dynamic equilibrium means. And this is how we would write that down. We would say sodium chloride with water creates sodium and chloride. While at the same time, I'm going to pick another color of highlighter. So this is the forward reaction. While at the same time, the reverse reaction is occurring. Sodium and chloride are coming together to form the solid sodium chloride. So the ions are forming the solid. So here's another way that we can write our equilibrium expression. We could use a double-ended arrow, and this double-ended arrow means that it's a 50-50 sort of reaction, right? The amount of NaCl breaking down into the ionic forms are the same as the sodium ion and the chloride ion reforming sodium chloride solid. I hope that makes sense. What do I have to ensure remains constant? I have to ensure a constant temperature, a constant concentration. So the water and the mass of sodium and chloride have to be the same. But the shape of these crystals, these salt crystals, constantly changes. Another type of equilibrium is a phase or state equilibrium. An example of this is ice and water at 0 degrees Celsius. We know that this is the freezing point of water. Freezing and melting point of H2O. So in this system, in an open, oh my goodness. So there are two things happening that you can talk about. In this case, this is condensation and evaporation. So water is moving from a liquid to a gas, and from a gas back to a liquid. It works in this because the volume of water remains the same. In this case, I don't have a lid on it. So it's an open system. And what happens is I have a lot more evaporation than condensation. I'm going to write it where it'll work. So we see a change in the volume of water. And that's what we mean when we say a phase or a state change. And lastly, what we can see is a chemical reaction at a constant temperature in, again, a closed system. So you have nitrous oxide plus oxygen to give you NO2. If it remains at 25 degrees Celsius, the forward reaction and the reverse reaction remain in equilibrium, releasing 75 kilojoules of heat. For carbonated beverages in a closed bottle or can, the amount of, this is carbonic acid. So this is CO2 in solution, is in equilibrium with carbon dioxide gas. And so as long as you keep the lid on your pop will remain carbonated because it goes from the acid form to the gas form and back again. You may have heard these, I know you've heard these in other science classes, homogeneous and heterogeneous. So homogeneous means the same, and heterogeneous means different. So a homogeneous expression means that all of the players are in the same state. So either aqueous, liquid, or solid. Or no, aqueous, liquid, or gas. If something is in the solid state, it's not useful because it pulls itself out of equilibrium. And this is when we're talking about chemical reactions. I know we talked about solubility being equilibrium. And we were talking about NaCl forming. This is not the type of equilibria we're talking about. Solid state would be important there, but not when we're talking about chemical reactions. So this is only about chemical reactions. Heterogeneous expressions have substances in different states. So you could have a liquid, or something that is aqueous, or something that is gas that reacts. Does that make sense?